Hey guys, how are you doing? This is Harsha. This video is about VLSI Interview Series. This is gonna help students prepare for their VLSI interviews in future, and we're gonna focus low power design right now. The questions are pretty standard, and it's more inclined towards a new grad role. If you like the video, please mention that in the comments. Here you go.
Good afternoon.
Good afternoon. How are you doing?
I'm doing great. Hopefully, hi Harsha.
Hi,
Good afternoon. Good afternoon.
good afternoon. How are you doing?
I'm doing great. Hopefully, you're also doing great and
Yeah,
everything going all right.
yes, everything is good.
Mhm.
So, can you please give me a brief intro? So, what are your degrees and what's your interest? And
Yeah,
those
sure.
things.
I'll go through my quick introduction and then we'll go from there. So, my name is Pavan Mandala. I completed my master's in electrical engineering at Arizona State University. I completed my undergraduation at Indian Institute of Technology, Palakkad, back in India, in electrical engineering. After completion of my undergraduation, I was very interested in the VLSI domain and wanted to pursue my career towards VLSI domain. So, in masters, I have taken courses such as digital circuits, analog circuits, computer architecture, VLSI design, VLSI architectures, and gained like knowledge on CMOS, FinFETs, different type of combinational and sequential circuits. Got the knowledge of timing, power, and also uh, like got the knowledge on ASIC design flow. Uh, and during these courses, I have done several projects like building the layout of adders, memory units like SRAM, and also I have done one major project that is building a GCN module using system Verilog. It is complete RTL to GDS flow project, and it's using EDA tool automation using TCL scripting. So while doing these projects, I have gained uh, experience on industry standard tools such as Cadence Virtuoso, Innovus, Synopsys Design Compiler, and uh, yeah. So here I am now with all my skills and experience. I wanted to, build my career or start my career in ASIC design, and that's why I'm here today. Thank you.
Okay, that's good intro.
Mhm.
Oh, so as this role is about ASIC design, so based on power. So
Yeah,
this interview, it's gonna be mostly on power. So I'm
Mhm.
gonna ask you a lot of power questions.
Yeah, that's okay.
I think you have good exposure to power and those things, right?
Yes.
So have you done any projects or like low power projects as such?
So in several projects, we were supposed to, optimize on power without compromising on the performance. It's not the major part, but projects included to optimize the power. Especially one project which I mentioned of building GCN module for performing machine learning on graph data. There we used uh, low power design in the RTL code and also optimized for power later on after completion of uh, the layout. We need to generate or we need to do the power analysis. There we have done, optimization of power in the project.
Okay. Okay, that sounds good. So I'm gonna go with uh, so typical power questions, and we can discuss in depth about all those powers
Yep.
associated in VLSI circuit. So my first question is like, what are the different kinds of power dissipations in VLSI circuits? So what's the
So,
basic power dissipation unit? Like terms? Yeah.
so in VLSI circuits, there are basically two categories of power: dynamic power and static power.
Okay, that's
Dynamic, dynamic power has two components: switching power and short circuit power.
okay.
So dynamic power dissipation happens when there is an active switching in the circuit elements, or rather transistors.
That's good.
Particularly when there is, let's say, a transistor is switching from high to low or low to high, there is some heat dissipation in the transistor due to its resistance, and there is some energy stored in the capacitor, load capacitor of the transistor.
Okay.
So combining that is the switching power, whereas in the short circuit power,
Okay.
when there is switching happens there for a fraction of time,
Okay.
there happens to be a short circuit from VDD to ground, and within the small interval of time there is a leakage of the power is dissipated, which is known as power short circuit power. And the other type of power is leakage power, which is mainly because of leakage current when the transistor is in subthreshold region or with on off state. So there are several factors for the leakage power, mainly due to channel
Yeah.
leakage.
Before going into that, so can you explain me that static term? So what do you mean by you explain the dynamic? That's good understanding and the way you explain good. But what's
Mhm.
the static power?
So static power, so when the transistor is off, uh, basically due to small excitation of ions, there is still some minimal amount of current is flowing through the channel, because
Okay.
either due to temperature, some atoms may be excited and still conducting the power, sorry, still conducting the current through the channel.
Okay.
And there are other sources of leakages, such as junction leakage, like from source and drain to the bulk, or gate oxide leakage, the current leakage from gate to the into the oxide into the channel. So majorly, the leakage we are talking about is the current flowing in the channel when the transistor is in off state. That is the main component of the leakage power.
Okay. So you explained me about leakage current, but what I want to know is, so why the term static came to that power static? So why it's a static thing? So can you think along that lines? Why the power is like called static?
Static in the sense that there is no activity in the circuit or the transistor. That is why
Okay.
it's in ideal state or in static state when it is in off. So that's why it's known as static power.
Hmm. Okay. So essentially, so there is no changing of bits or changing of signals around the transistor. So
No activity.
yeah,
Yes.
yes. Uh, so power. So what's the formula for uh, leakage? What's the formula for the leakage power?
So I off is mu into W by L. Give me a second. Let me recall it. Uh, so mu Cox W by L into 1 minus e power minus VGS minus VT uh, by NKT into, sorry, it's
So that's fine, I guess. You just need to know the proportions. So
e
is it
power.
like
Yeah.
directly proportional or yeah? I got you that you know the basic formula. So
Mhm.
so what's the factors leakage depends on? So how can you reduce the leakage current if there is
So
in the circuit?
so there are a few factors. Leakage depends on mainly.
So based on gate level, I need the gate level
Yes.
technology
So
level as of
yeah.
now.
Okay. Sure. So the on the transistor level, the leakage mainly depends on the width of the transistor and also the threshold voltage of the transistor. So when there is more width, there happens to be more electrons or holes that are excited, which will be adding up to more leakage. And also the threshold. Whenever the threshold is high,
Okay.
there is less leakage, but whenever the threshold is low, there is more leakage. So the threshold is the minimum amount of voltage required to have the inversion in the channel. So at minimal threshold voltage,
Okay.
there are more carriers, charge carriers excited, and will have more leakage in the channel.
Okay. And I think did you also tell about temperature?
Yeah. So temperature on, like, normally when the temperature increases due to scattering phenomena, the sorry. So normally when temperature is increasing, we'll have more leakage. But whenever in the typically when we are talking about lower technology nodes, with the increase in the temperature, there is the threshold voltage will be decreasing, meaning there will be more leakage in the circuit.
Okay, more leakage. So do you recall any phenomenon like temperature inversion of such?
Yeah. So temperature inversion, like it's the inversion relation to the delay in the lower technology nodes. Ideally, when there is increase in the temperature due to scattering phenomena, the delay in the circuit or the transistor increases,
Okay.
slowing down the charge carriers. But
Okay.
in lower technology nodes, the dominant factor will be threshold voltage. So increase in the temperature will be, like, will lead to decrease in the threshold voltage, because at higher temperatures, more and more charge carriers are excited and available for the current conduction, and that will be the major factor. Hence, there will be delay in the decrease in the delay through
Increase the
the
delay.
channel.
So okay, that lower temperature nodes, if temperature increases, the delay
It
decreases.
decreases. So that's an inversion relation to the temperature. That's why temperature inversion occurs to lower technology nodes.
Okay. Mm, so so do you recall any leakage reduction methods? So we discussed about the gate level parameters or technology level parameters. So
Yeah.
can you recall any leakage reduction methods? So like the
On
method
gate level, on
or
the
like
technology level, or normal at any
yeah,
level.
you can like uh, tell a way how do we do, and you can also describe is it like a technology level or the system level or architect level, etc.
Okay. So on the transistor level, we can improve the leakage through increasing the threshold voltage of the transistor. That is basically we can play with the bulk voltage of the transistor. So if we decrease the bulk voltage, uh, meaning ideally on an NMOS transistor, the bulk and source are at same voltage. That is when they are at the equal voltages, we call that as nominal threshold voltage. But whenever bulk is at different voltage, the threshold voltage will be changing. So when we have a negative bulk voltage, we can increase the threshold voltage of the transistor. Hence, we can
Hmm.
reduce the leakage current that is at the transistor level or the technology level.
Okay.
Another thing we can do to stop the leakage is mm, sizing also constitutes for the leakage. The higher size transistors have more leakage, but they also offer more performance. But if we are more concerned towards the leakage, we will scale down the transistor sizing. That thing, that is one thing we can do. On on a circuit level, there is a technique called power gating to
Okay.
decrease the leakage current. So basically, when a certain part of the circuit is in like ideal state for a while, we
Yeah.
can cut down the power supply to the circuit
Okay.
elements
Okay.
by adding high threshold transistor elements
Yes.
between the circuit to the power supply,
Okay.
and which is operated using an enable signal like sleep signal.
Okay.
So whenever there is activity, we can a- like uh, turn on the signal, but when there is no activity, we can meaning using the enable signal, we can turn off the signal.
Yeah.
There
Awesome.
is there will be still leakage, but it's very minimal compared to previous scenario.
Okay.
So we will be choosing the cell transistors with very high threshold, so that
Yes.
there will be very less leakage in the circuit.
Okay.
That is one technique we can be using uh, to reduce the leakage power.
So do you know any other methods?
Uh,
If
Other ways are mm,
you know, that's fine. No, it's
I just thinking what are the factors. So we can like change the operating conditions. If let's say my voltage is low, then we can have a partly decreased leakage current.
so voltage is low. So what do you mean by voltage? Which voltage you are talking about?
In the supply voltage,
Oh, you mean the VDD, right?
yes,
Okay. So you can decrease the okay. Oh,
and also
VDD.
as we said, yeah, as we
Accommodation factor, I guess. Okay.
sorry.
Further. So what's the trade-off? I was like just curious. If you reduce
So
the
yeah, if we reduce the VDD, we'll be getting less performance out of the chip. But
yes,
uh, strictly speaking, if we are mainly looking for lower power consumption, then that might be the option.
yes,
Again, given that we meet the timing requirements due to the lower performance, but that is one thing we can do, and also operate under operating conditions such as temperature. So operating at lower temperatures might help the leakage.
yes, got you. Uh, so have you heard about this thing called stack effects?
Stack effects.
So it's like
I
a
don't
gate level leakage reduction technique.
stack effect.
It's like that's fine. So it's like stacking transistors and reducing the leakage power. So
Sorry, I don't recall about it much.
okay. So we discussed about static power right now. So it's like a good brief
Yes.
about all those methods and those things. And
Yeah.
right now, let us go to dynamic power. So
Okay.
so you told there are like two components, right? Switching and short circuit. So can
Yeah.
you elaborate about the formulas and what are the factors to reduce individual those powers?
Okay. Sure. So the switching power, switching power has a formula of alpha into capacitance, load capacitance into supply voltage square into frequency of this operation, at which frequency we are operating. So to decrease the switching power, we need to uh, basically concentrate on these four powers. So basically, switching circuit is the more dominant power dissipation in the circuit compared to other two. So and it's like quadratically depending on voltage. So it's like proportional to VDD square.
Okay,
So unless and until we need these high performance, we can do or operate the circuit on a lesser supply voltage, lesser VDD.
okay,
Uh, the Okay, I'll go online. So alpha, which is our switching factor.
Okay.
Whenever there is a switching activity, that will, let's say, uh, for example, clock. Clock is the most power consuming component, sorry, power consuming factor in the switching power. So whenever, let's say, to control the switching of this clock,
Okay.
do what there is a method called clock gating,
Yes.
and other methods are like using the techniques called gray code, uh,
Yes.
which has like minimum transitioning from one state to the next state.
Yes.
So clock gating ideally, so whenever uh, let's say a circuit doesn't need like is not changing and is sitting ideally, so there is no change in input to the output, then we can stop the clock to the part of the circuit so that we can save some power there. So to do that, we to implement the clock gating, there is we generate a signal clock signal. One way to
Oh
generate.
yeah, let us discuss about the factors. We can discuss in depth about those things. Uh, so you told like we can use encoding, like gray encoding and clock gating. So
So
is there any other things you recall, or else you can also discuss about other parameters?
yeah, so for now I recall these two, and to control the capacitance of load capacitance, we we have to choose the circuit or build a circuit with less fan out.
Okay.
Uh, so if the circuit has to drive lesser number of components, then we'll have lesser capacitance required. And okay, and with to decrease one other way to decrease the dynamic switching power is to by controlling the supply voltage VTD, which has the quadratic dependence. And also there are to decrease the frequency, there are two famous what do you call methods,
Yeah.
like DFS and DBFS. So dynamic voltage scaling and sorry, dynamic frequency scaling and dynamic voltage frequency scaling. So whenever we don't need to operate the circuit at highest frequency, or we can turn down the frequency to save the power. But one disadvantage for DDFS is it only saves the energy but not the power. But
Saves only energy but not the power. Okay. So it's a DFS or DBS. So what are you talking about? Which saves energy, not power?
just a second.
Yeah.
Mhm. So DFS. Um, so we are slowing down the circuit, but ultimately we will be doing the same amount of time in larger time frame.
DFS.
So
Okay, we are doing same amount of work in larger time. What do you mean?
so energy is same, but the power energy per unit time is less. We can decrease in the power.
Okay, I think per clock cycle you are talking, right?
Yeah.
Per clock cycle we can
No,
decrease.
yeah.
So
So,
DFS means essentially decreasing the frequency. So
mhm.
so what do you
Frequency.
think per clock cycle? What's the power?
Just a so you are like you are asking a question for me.
Yes. So you are like telling that DFS saves power but not energy. So I want you to explain on that. So why?
Okay. So when we operate a certain part of the circuit at lesser frequency, meaning my time period is going up. So
Okay.
now, uh, let's say we have to perform X amount of work, or let's consider in technical terms, let's say we need to perform an addition. But to perform an addition, we don't need to have the highest frequency, or we can run at lower frequency, meaning we have more time to do the work.
Okay.
And ultimately will be the energy used will be same, but now we are okay, my time period is increasing, so energy, so power, what is it?
Mhm.
So power is energy over time, energy over unit time. So as my time period is increasing, now my power will be less. Power consumption will be less per unit clock cycle.
Per clock cycle, your power essentially will be reduced. Okay.
Yeah.
What about the energy?
Energy will be like to complete a task, the energy will be same. But we will be taking more time. That's it.
Okay, that makes sense. So that's DFS. So DVS saves energy, but not. I didn't get it. What's that use of DVS?
So DVFS, so dynamic voltage and frequency scaling. So now we will be controlling decreasing both voltage and frequency.
Okay.
I mean, so decreasing frequency will decrease my power, but now we are operating at lesser voltage, so we will be saving on energy as well.
Yeah. Okay. Overall energy will be saving. Okay.
Yeah, yes.
That makes sense. Okay. Okay. Essentially, what's the trade-off using these two methods?
My circuit will be slower.
Yes.
But as I said, if we are mainly focusing on same power, then these are the two efficient techniques that are used in the low power design.
Okay. So that makes sense. So I want also your opinion on this pipelining and parallelism. What do you think? Will those methods benefit our circuit in power?
Just give me a second. Sorry, madam. Yeah, you were asking something.
So I was asking about pipelining and parallelism, whether this can benefit circuit in power. So I was, what's your opinion on that?
So using pipelining, we can save time using pipelining or parallelism. So those are the techniques for performance to gain more performance. And if we are getting more performance, then they will be.
So let me take you this way. So let's say there is a circuit with frequency f. So can you do pipelining on that circuit? So finally, the frequency is the constant, or that's a desired frequency. So based on that, you can answer my question. I think that would be more reasonable way. Having a desirable frequency f for a given circuit, which already achieves that frequency. So if you do pipelining, it does that. So can you think of something?
Yeah. Using pipelining, frequency. Missing something. Yeah. So with pipelining, we can operate the circuit at lower frequencies because we are breaking the circuit, and that will help the power consumption.
So we are breaking the circuit. What do you mean by that? So breaking,
meaning, suppose we, let's say, we're considering a path which takes a time period of t, and there are let's say 2 gates in the path. Now pipelining, with the help of pipelining, if we add a register between the gates, now the minimum time period that I need after the pipelining is the time required for 1 gate instead of 2 gates. So now I can do, or I can decrease my frequency calculatively.
Okay, you can reduce the critical path time, I guess. Okay.
Yeah, and that will help me in decreasing the power.
Okay, so essentially you can operate at lower frequency, right?
Yeah, I can operate my circuit at lower frequency. That will, as we have less frequency in the circuit, then that will ideally reflect in lower power consumption, particularly switching power.
So decide frequency. Okay, so let's say, so I think so let's say if our circuit wants a desired throughput, let's say, so if you reduce the frequency, if we pipeline the circuit, we can still,
so using pipelining, my throughput increases.
Yes, so essentially you can get the same throughput as before by reducing the frequency of the circuit.
Yeah, and also, so we are extracting more performance there. and also with less power.
More power. Okay. So what's the power you are
Actually,
saving on? Okay.
switching power. Switching power we are saving.
Okay. Is there any other powers you are saving or introducing in the circuit?
So we'll be also saving in the leakage power.
It's saving on the leakage power.
Uh, like
So why do you think that leakage power is saved?
mm, like let's say the example that I gave, if my critical path has two gates,
Okay.
the second gate will be waiting ideally until the first gate outputs its signal.
Okay.
But if we do the pipelining, we
Okay.
can operate both the gates parallelly. So time, the ideal time for which the second gate was sitting, we can cut down there. Meaning, so the there, so like we're cutting down the ideal time main, for the second gate.
So you are telling that. So we are cutting. Okay. From the ideal time. Oh.
So now let's say the second gate will wait until the first gate
So can
produces
you tell
its
me the
output.
parameter? So in the leakage power. So is that parameter including the leakage power formula or so?
No,
Because the frequency you're telling that essentially the frequency influences the leakage power, but we see the frequency term in dynamic power, not in the leakage power. So why do you think that's not been a
so
factor?
mm, so I'll just put my thoughts into words properly, then maybe you can get a clear idea.
Okay.
So okay, now we are talking about two gates, right?
Yes.
So suppose before pipelining, we have the critical path as two gates, so meaning delay of gate 1 plus delay of gate 2 should be within the time period. But suppose my gate 1 has certain delay, and within that delay my gate 2 will be sitting ideal. That will uh, constitute for some leakage, and whenever my gate 2 is performing its activity and during that delay time gate 1 is sitting ideal, uh, and there will be some leakage. But if we achieve the parallelism or pipelining, we can operate both the gates parallelly, and there will be no ideal time for the leakage. That's what I'm.
So let's talk about pipelining here. So if we do pipelining, so we can perform.
Yeah, that's one. If sorry, could you like be more specific on what you are asking? I'm sorry.
So you're telling that if we do parallelism, pipelining, so we essentially decreasing the frequency of the circuit. But you also saying that so we save dynamic power. That's fine. So you also saying that we save leakage power. So you told that it's because that if there are like two gates in a path, if a gate, so so second gate in the path has lesser time to get the data, because if we do parallelism on that path, then what you told makes sense for me as of now. But what I am worried is, so there are like a lot of other paths which are not pipelined and no, which are operating at lower frequency right now. So did you get my point?
Which are operating at lower frequency.
Yes, there are like a lot of other parts. So
No,
there are
so we are not doing the pipelining on other parts, right? I'm just
other paths. So
like.
but they are operating at lower frequency.
Mhm.
So that means the delay is getting increased, right?
Yes.
So that means that
Delays.
essentially increases leakage power on your basis you told, like as on the way you approached. So it shouldn't make sense if you get me.
So
So you only
yes. Okay.
thinking about the critical, so only the pipeline parts. What I'm
Okay.
telling is there are like a lot of not pipeline parts which are now operating at lower frequency.
Okay. Uh,
That would increase leakage power essentially based on the approach you told me. So did you get my point? So what do you think the approach you told? So if
So
there is
basically,
Hmm.
the main point I was trying to make is so there is no particular, let's say, delay element in the pipeline. With the pipeline, there is an extra component. So here and there, we might get a similar kind of delay, but my throughput is increasing in the critical path. But there is like not necessarily a like decrease in the delay because of pipelining.
So if you're operating on same frequency, or are you reduce? So let's say we have a circuit with frequency f and throughput t.
Mm-hmm.
So if we pipeline that circuit, so that to make sure the throughput is similar to the before circuit, which is not pipeline.
Mm-hmm.
So what we have is, no, we can decrease the frequency. We can operate on reduced frequency to achieve the same throughput, because
Yeah.
we essentially pipeline the critical path, I guess.
Yes. Yeah.
So we reduce the frequency in the newer pipelined circuit to achieve the same throughput, or let's say performance. So as we are reducing frequency, what we are saving is like dynamic power, as you said.
Yeah.
We are reducing the switching power. So I'm also asking regarding whole circuit. Are we saving on any other powers, or are we introducing some powers in the circuit?
Okay. So you are saying because we are reducing the frequency, my delay will be increasing, and based on what I said, or
On your
applying this,
approach?
on what I said, the leakage power should increase. Is that
Yes.
what you're saying?
Yes. Based on your approach, you said me that pipeline paths would decrease the leakage power due to the logic you said. I could decrease the delay of a signal to receive the second gate, which is like not pipeline before.
Mhm.
So I would say like there are like which are there are parts which are not pipeline. So if I think about those parts, essentially the frequency is less, so the delay is more. So yeah, that's what I'm thinking.
Mhm. I still can't figure out like what because ideally, if I I am having more delay in the circuit, based on my approach, you're saying that leakage should increase on the other parts.
Yes,
Uh,
because essentially frequency is less, right? So the time for a signal to reach a certain gate no increased.
okay.
You got my point, right? So the delay increased. I mean, so if there are like two
Okay.
gates, let's say, so the time for a signal to go from gate A to gate B right now increased, because we are operating in lower frequency.
Okay.
So
So
what
you're
I'm saying,
saying.
based on your approach, what do you think? Is it right in the perspective of overall circuit, or yeah, that's an interesting thought you put there. But yeah,
Mhm.
but I also wondering if that saves leakage power
So
pipeline.
no.
But
So basically, the I was like thinking of like different regions of circuit operating at different frequencies.
okay,
So the pipeline circuit will be operating at different frequency to save the power, but not the entire
oh,
frequency.
so I have a quick question here. So let's say you pipeline a critical path.
Mhm.
So do we need to essentially operate other parts of the circuit at the similar frequency, or we can reduce the frequency overall, or
We can
just
reduce the frequency overall.
overall, right?
Yeah.
So let's take it simple, and let's consider that we reduce the frequency for overall circuit, not
Mhm.
just the pipeline region or those kind
Oh
of.
yeah. Oh sorry. Yeah, I got you now. Okay.
So
And
we can discuss if there are any other powers in that circuit, or so what's your approach in that? So essentially, doing pipeline, what are the trade-offs we are having?
so yeah, with decreasing the frequency, we are increasing the power, but
Or I guess okay.
Mhm. And also, yeah, now we are decreasing the frequency, we are decreasing the switching activity, meaning we can also save on switching power.
Okay.
And if we want to be more specific on what's happening on leakage power is decreasing the frequency, we are increasing the time period. So the components which are not in the critical path will be sitting ideally for wait. No.
So we are adding flops, right? So if we are adding flops, considering the dynamic power equation,
Mhm.
so there are like clocks to the flops, right?
Yeah.
So does that affect dynamic power, or does that affect any parameter in the dynamic power?
So we are adding extra element. It consumes some power and also it consumes some area. And
Okay, let me take this. Okay, okay. Oh, yeah. So let's say I have two circuits, circuit A, circuit B. Circuit B is pipeline.
Can you give me a second? I'm very low on my laptop battery.
Okay.
Ah, I'm also grabbing just a pen, paper. Just yeah, go ahead.
Oh, yeah. So let's say we have same throughput, but yeah, circuit A, circuit B.
Mhm.
But there is like frequency downscaling from circuit A to circuit B. Two same circuits, we just pipeline the circuit.
Okay.
Same throughputs, but there is only reduced frequency for circuit B because it's pipeline. So I want to know your analysis. What are the different powers you are saving, and what are the parameters, or what are the trade-offs adding pipelined registers overall, or is like for performance, area, or all those things.
Okay. So I'll just go from bottom to top. Obviously, we are adding extra components, so my area will be increasing due to pipelining.
Okay. And I will also try to introduce you to an interesting point here. So you can also think about reducing the supply voltage. Can we reduce the supply voltage in the pipeline circuit? What do you think? So you can think in terms of DFS and DVFS, the methods you told me. So but essentially it's not dynamic. That's what I think.
Okay. So I just want to what you call correct or point out a thing.
Okay.
So because of pipelining,
Okay. So generally, where do
usually
you pipeline? So just quick question. Which parts do you pipeline? Yeah.
the critical paths.
Yes.
So now, if let's say my critical path has a time period of t for
Okay.
a particular frequency f. Now I'm pipelining, let's say halfway uh, for easier understanding.
Okay.
Now, ideally, let's say if we are pipelining ideal like in the middle, so left two equal, we are left with two equal circuit elements. That's what I mean to say.
Okay.
Now the required time period is reducing, right?
Yes.
So if my time period is reducing, I can operate at higher frequency.
If you are, so you can operate at higher frequency. Yes.
So so if we are doing pipelining, my frequency is increasing.
So we can operate at higher frequency essentially, but what we want to do here is save power. So
Yeah.
to save power, and we know that our only requirement is throughput to be the same. So think in those terms. Do we really need to increase frequency now?
So now my so usually the main purpose of pipelining is to increase the throughput, right? So,
Yes, increase the throughput.
but if we are to do or to have the same throughput,
Okay.
okay, now
We can decrease
yeah,
frequency. Yeah.
okay,
So how does that save in power? That's the main question.
okay. So if we are decreasing the frequency, my time period is increasing. Let's say from t to t. Okay.
So think in terms of overall circuit.
So now if we decrease the frequency, my time period is increasing, means I am getting very less performance through my circuit. My area is increasing, my performance is decreasing, but my power.
Performance is same because the throughput is same, right? As compared to before circuit. So essentially you are
No,
not degrading performance.
so yeah, as you said, only the performance of the pipeline path is.
So I'm telling you to think overall circuit and I need the parameters for the overall circuit. So essentially the throughput is same, right? So can you think throughput as a performance factor? So
Yeah, so it is producing every output with. Just to be on the same page now.
okay.
Okay, I'll just. So throughput, it is the time required to produce each output, right?
Time required to produce each output. Yes.
And basically with the pipelining, throughput increases. So, but we are keeping the throughput same. And to keep the throughput same, we are decreasing the frequency, means we are increasing time period of the circuit of or the
Yes.
pipeline path.
Of the clock. Okay. Of the clock. Time
Yeah,
period of clock.
yeah, of the time period of the clock for
Yes.
the pipeline path.
For
Or
every
basically, if we are concentrating just on the pipeline circuit here. Now, if we increase the time period,
okay.
meaning we are increasing the time period overall, right?
Yes.
Now, now, if we are increasing the time period overall, what I am saying is we are increasing the delay rate.
So just comment about dynamic power. Why are you saving dynamic power? First thing.
Why are we saving the dynamic power? Like on which terms you're looking for? Like,
So yeah, so I want to comment. So which terms we are saving on? Let's say dynamic power. So there are like different terms in the dynamic power. So comparing to circuit A, okay, how are we saving dynamic power?
to frequency,
So essentially we are operating lower frequency. So
we are saving dynamic power there.
how is like dynamic power proportional to frequency? It's like proportional or
Linearly proportional
yeah,
to frequency.
directly proportional. Yes.
Oh, sorry, meaning directly proportional. So if we reduce in the frequency, we will be uh, reducing the dynamic power.
Okay. We can
And
also think if we are saving the switching alpha. What do you think?
yeah, so that's what I just wanted to go there. But before that, now the switching factor also decreases because we are uh, operating as less frequency. So my clock is switching at a lesser rate than usual.
Okay. But is that switching activity is related to switching rate or amount of switching you do in a clock cycle? What do you think?
Switching is,
So let's say if you have
okay, okay,
encode.
okay, okay, okay. So if denominator is high, yeah. So switching is like the average number of or the probability a node switches within
Okay.
a clock period.
Okay.
And now we are saying we are increasing the clock period, right?
Okay.
So my switching probability decreases, right?
It's like the average time the switching occurs. Mm,
Okay, okay.
telling switching activity reduces.
Sorry, my switching activity increases because we are having more time period.
Increases.
Yeah. Mm. Sorry, I will cut that.
Okay.
So switching factor is the average number of times a node switches within a clock period.
Okay.
Okay.
Mhm.
Now we are increasing the clock period, right? We are reducing the frequency, we are increasing the clock period.
Okay.
Now because
So let us take this way on a non-pipeline path, which is same to the before circuit. So what do you think of switching activity on that path? Let's not consider this pipeline, all those things. Let's think of non-pipeline path with decreased frequency. So do you think the switching activity on a particular gate reduces due to decrease in frequency?
yes,
Also, why?
because we are operating at lower frequency.
Okay.
Now we are running at a lower clock rate, so everything the activity slows down.
Activities.
Because let's say if we are taking a path between flip flop to flip flop, my clock cycle on a positive edge, if the flip flop is triggered.
Okay.
On initial case, let's say before decreasing the frequency, my time period is t, and the next clock period hits at t, right? But if we are decreasing the frequency in the second case, or my time period, it's assume it has to be 2t.
Okay.
And so in 2 time periods, we are getting only 1 clock edge instead of 2 clock edges, which we are getting before.
Okay.
So now the activity has come down, right?
Okay.
Are you like
So I'm
you
getting,
understand that, or you?
I'm getting how are you approaching that?
Mhm.
But so what I want to tell is, so if there is a gate, if there are, let's say there are like two switches in that gate, so you mean, so there are like let's say there is an AND gate.
Mhm.
So in a certain clock time period, let's say t, so there are like two transitions at the input of the gate. So can I talk about an AND gate here, or should I? Yeah, I think I can. So AND gate, there are like two transitions in the input signal. So let's say it's like 0 to 1 and 1 to 0.
Okay.
In different time frames.
Yeah.
Let's say t2.
So let's as I said before. Mm,
So number of switching activity, let's say, no, is it two or switching activity? What do you think? Is it like the transition? So input does two transitions, like 0 to 1 and 1 to 0, on an near an AND gate in a certain time period t at t1 and t2. So what do you think the switching activity is on that time period? Maybe
So
is it like how much time it switches, or what's the time it taking to switch, or
no, it's not the time taking to switch. It is like number of transitions it is making.
the number of transitions it is making?
Yeah.
Or so essentially, if you increase the time period, so the number of transitions still remains the same. That's what I'm getting at now.
Yeah.
What do you think?
Okay. So yeah. So I got it now. The switching is same in both cases.
Okay, think about that. So apart from that, what do you think? No, can we operate our circuit at low voltage?
Low voltage,
Yes.
like on
Low power.
without compromising, or
Didn't get you. What happens?
in the voltage. Is that
So
right?
can we?
Yeah. Continue, please. So you are saying how are we, like, what are the effects of decreasing the voltage? Is that
So
right?
can we reduce the VD supply voltage now on compromising on frequency? So what do you think?
Without compromising the frequency?
No, with compromising. So I am giving some leverage on increasing the frequency so that we can decrease VDD. Because if we decrease VDD, what happens? The critical path delays increase, right? What do you think?
Yeah.
So what I'm saying is, if I slightly increase the frequency, and reduce the overall supply voltage of the circuit,
Okay.
what do you think? Does that save power? Can I do that first thing?
So you're saying I am increasing frequency little bit.
So from circuit B, we are going to circuit
Yes,
C,
yes.
let's say. Okay, yeah.
I got you. So let's say for the circuit A to the circuit B, let's say we decrease the frequency by 2, f by 2. Now you're saying I'm increasing the f by 2 to, let's say, 3 f by 4 or something like that.
Okay.
And we are getting some performance there, but instead that, I'm decreasing my supply voltage.
Why are you doing that? So to maintain the same throughput, let's say.
Yeah.
We can we can go to certain lesser VDD.
Yes.
Okay. So now what I want to comment is, so is that useful when compared to circuit B?
Yes, it is useful because the power is linearly proportional to frequency, but if you decrease in the voltage, it is quadratically proportional.
Okay. 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 It saves power.
Yeah.
More or less that thing. So if we increase, so if we decrease VDD, what do you think of leakage terms? Is there any effect on leakage?
Yeah. Sorry. My leakage also, my leakage current also, or leakage power also goes down, like decreases.
Okay. So essentially, so there is this concept you said like DFS, DVFS, right?
Yeah. Yes.
So what's your saving on one and not saving on other? It's like the energy you said it was like we are saving in DVFS, right?
Yeah. Yes.
So in the present circuit, so if we scale frequency in the circuit B, so what's the thing is overall our total energy consumption would be same.
Yes.
But yeah, if we think of circuit C, what do you think? The energy consumption decreases.
You're also saving also energy. Okay.
Energy. So that's the main factor, the total energy consumption of a certain circuit, right?
Yes.
So that's an important thing to remember. And we are also, so it's because we are cutting a lot of powers like leakage power, dynamic power quadratically. That's how you are entirely saving on that energy. That's right.
Okay.
So can you explain me what's a clock gating circuit and how it works?
Clock gating circuit helps in power reduction method for dynamic power. So usually when a circuit sits for ideal for a certain period of time, the clock that consumes more energy will keep on be feeding to the circuit, and if we cut down the clock to the circuit, we can save power because we are stopping the transitions of the circuit. Uh, sorry, we are stopping the transitions of the clock to the circuit, and in order to do that, we will implement a clock enable circuit that will be passed on to a negative latch to avoid any glitches from the circuit, and then that output of negative latch will be passed on to an AND gate, for which another input is clock, and the final output of the NAND is fed into the circuit, which acts as the clock gating circuit. And for the clock enable, usually we can use a XOR gate from input to the output of the circuit part, which we are preparing to implement clock gating on.
Okay. So to do clock gating, so what are the basic criteria you look for the flop you want to clock gate?
So basically, clock gating works, or we can save power only if the circuit is ideal for larger amounts of time, and because it comes at the cost of extra area and extra circuit elements that we are building upon. That is the main criteria we need to look at to implement the clock gating.
Okay. So clock gating, you told you will be using a latch, right? While implementing the clock gating circuit.
Yeah.
Can you also use flip flop there?
Yes, we can also use flip flop, but to make it simple, and flip flop is additional circuit elements required to build a flip flop. So just wanted to put down what do you call it, to save, if we want to save a little bit of circuit elements and area, then we can implement through latch. We can also use flip-flop though.
Okay, makes sense. So you want to use the negative, right?
Sorry?
Which kind of flip-flop, like which sensitive level? Is it like positive, negative?
Negative.
Yeah, yeah, that's good. So coming to power gating, so what do you can you explain me briefly about power gating?
Yeah. So power gating is in power optimization circuit that we build to stop the leakage power or to reduce the leakage power. So let's say if any of my circuit elements are in like off state, and if we need to cut down the leakage current that is going into the transistors, we can add two cells like an isolation cells which have high thresholds voltage for them between the supply nets and the circuit elements, and can be operated using a signal like a sleep signal. So whenever we don't require the circuit elements, we can on the sleep signal, so that the current can be saved, because these cells which we are using for power gating is have high threshold voltage, hence the leakage power will be less, and very less leakage current will be passing through the transistor to that circuit, and so we can save the leakage power abruptly, meaning we can save most of the leakage power.
Okay, so let's say you power gated a certain area in a circuit.
Mhm.
So if you want to transfer a signal from one power domain, that's the power gating domain you have
Okay.
done to the circuit, and to the non-power gating circuit. So it's like you have two different power domains. You want to send the signal. So
Yeah.
what do you think? Can you send the signal directly from one power domain to?
No. So if we send the signals from one power domain to other power domains, because the operating voltages are different in these power domains,
Yes.
it can give us trouble and change the functionality or even change the functionality of the circuit. So usually there are a circuit element called level shifters used in the digital circuits, either upsizing or downsizing. Or level shifters are used depending on the required. Depending on necessity. So level shifters are used. I are the one circuit element that are used in before sending to other domains.
Okay. So if so, I have this question. So if there are like two power domains in a circuit, in a big circuit,
Okay.
uh, if they are operating at, if they are having same operating voltage.
Okay.
So what do you think? Can you still send the signal from those power domains directly?
Same operating voltage, you said?
Yes, which share same operating voltage.
So ideally no, because the voltage drop through these the power getting cells is high, because we are using these cells with high threshold voltage. Hence the drop will be low, even though we are having same voltage in both the circuits. The output has lesser voltage compared to the other domain, because of the voltage drop across the uh, isolation cells used in power getting.
Can you explain me again why isolation cells came?
Meaning isolation cells in the sense the cells that we used for power getting between the power grid and the circuit. So
Okay.
these cells are having higher threshold, and in
Okay.
case of on circuit, the current should be passing through these cells, which I meant as isolation cells, and because of its high threshold nature, the voltage drop across the cells will be high, and then that voltage drop is considered, is taken into this power getting circuit, which is why we will be having lesser voltages at the outputs.
Okay. So, but still they are operating at same voltage, two power gating cells. So, uh,
So I'll just give an example. So let's say now if my power getting cell or my power getting circuit gives an output of high. So let's consider simple a NOT gate, and
okay.
so for the NOT gate, I am attaching a like a inmost transistor from the power grid to the NOT gate. So suppose my output of the NOT gate should be high, and that has to be passed into the other power domain. Now, so let's say for the output of the NOT gate to be high, the NOT gate should be pulling down the charge from the VDD.
Okay.
Right. So when the NOT gate pulls down the charge from the VDD, so there is essentially a voltage drop across the transistor because of the high threshold.
Okay.
And let's say now if my VDD is 1 volt and the threshold volt of the uh, the transistor is 0.3. Now I will have a drop of 0.7, and due to its own threshold, we might get output of 1, but the actual voltage might be around between 0.6 to 0.7 volts. And if I take that to the next domain, and let's say another inverter,
Okay.
now due to noise margin, and if the noise margin in the other circuit elements is not that high, that 0.6 voltage will not be enough for the other part of circuit to consider it as logic high, so it can be logic low, and we will have the functionality changed there.
Okay, makes sense. So I have this question. So if there are like two power domains, okay, which are operating at same voltage, same operating voltage. So power gating, we can so there will be like, I guess there will be like enable signal where we can on the power domain or switch it off. So if one power domain is off and other power domain is on for the same operating voltages, so what are the measures you take when you are sending a signal from those power for those circuits, from those circuits? So what is the additional circuit you will add, or what you're gonna do so that the signal doesn't corrupt or the noise margin is good?
Okay, so you're saying if in one domain where we are doing the power gating, if the circuit element is off, and we are
Okay.
working on,
Yes.
and we are working on the domain where the circuit is working.
Okay.
So
Yep.
because of this off, we might get unwanted signals, and that might correct the second power domain circuit. That is what you are trying to ask, Harsha?
Yes, that's essentially that's the thing.
Okay.
So if we add on power domain in one circuit, if the power domain in other circuit is off, but still they both are operating at same voltage, same operating voltage,
Mhm.
what are the measures you take, or do you need to take any measures while sending signal from those circuit? Or
I just wanted to have some clarity here.
okay,
So we are in let's say in the first domain, our circuit element is in off state, and because of its off state, we don't need any signals. The circuit element can't send any signals. If I'm getting this right, or I just wanted to have some.
just the power domain is off doesn't mean it doesn't get any signals. So it essentially means we are not interested in power gating in that. Uh, in that particular circuit. So when we do power gating generally,
When
do
it's
we do that every time or
okay, no, meaning so the power gating we do in the sense we are on like using it currently or not, or
so I want to do one more thing. So we do clock gating when there is no change in input signal, right?
yes, input or yeah.
What about power gating?
When my circuit element to which the power gating is being done is in off state, so no output is produced from the circuit element.
Yeah. So when there is no output is coming, so
Okay.
we generally do power gating for long
Okay.
time. Yeah.
Okay.
So first one is so let's say so there are like two circuits A and B.
Okay.
So if first circuit is not power gate, so we can always make a particular power gating circuit to be on or off, I guess. Do you think a circuit has that flexibility?
Yeah.
So if we do power gating, if we don't do power gating on circuit A, and if we do power gating on circuit B,
Okay.
but if they are having same operating voltage,
Okay.
what do you think? Can we still send the signal like that, or do we need any special circuit in between?
Okay. Maybe I
Those things
think I
are
got your
like
question.
directly connected. Yeah, those things are direct. So if there is zero signal, also you still need to send the signal to the next circuit, right?
Okay. So
So one thing, have you heard of this isolation cells, which can be used? Uh,
for power gating, you said, or
so while transferring from one power domain to other power domain, can we use some isolation cells in between? Have you heard this kind of thing in your master? Or,
I I don't remember much, or I can't remember right now much about the isolation cells. Uh,
okay,
I
that's
think
fine.
I don't
That's fine.
have much
Then
about.
if you don't know about it, that's fine. So it's like for power domains which share same operating voltages.
Mhm.
So some of the power domains may be shut off.
Okay.
We don't know. So generally, an isolation cell is required on the power domain interface. So
Okay.
that's
So the signals will not be interfered from that power domain. Is that
yeah,
it?
yeah. Because when there is cells which are connected to power off blocks,
Okay.
their inputs may become floating, which may cause high leakage power, something like that.
Yeah.
So
So okay.
the
So
point is
this
isolation cells are required, necessary to isolate floating inputs. That's it. Isolation cells are required to necessary.
okay. So basically, these isolation cells will reduce or will completely cut down the even the leakage current or something like that, right? Or
Yeah. Yeah. The,
I got you.
yeah.
I'll have a look
Yeah.
over that.
Yeah. You can
Thank
have
you.
a look over that. That's it.
Thank you.
I think that's it out of power gating.
Thank you.
Okay, that's it. I think regarding power from my side, not much. And so yeah, just one more thing. What do you think of parallelism?
Parallelism of my circuit.
Yeah, so there is like
Sorry.
pipelining and parallelism. So what do you think of parallelism?
So in terms of like saving power or general.
Yes, same power. And generally, what is power parallelism? So what's that?
So parallelism, we can do parallelism. Parallelism or will how can you say as
So pipelining is like putting resistors between a combinational path. So yeah,
yes.
same thing. Yeah, parallelism. What do you
So
think?
parallelism, like we are operating multiple tasks in parallel in a single clock cycle. So that will be consuming more power compared to an initial case.
So let's say we have a circuit A before.
Okay.
So circuit A is like a smaller part of a bigger circuit, and we want to build a parallelism for that circuit A.
Okay.
So what do you think parallelism is in the perspective of hardware structure, maybe?
So what I am thinking right now about parallelism is, let's say I have two tasks to do.
Okay.
So instead of doing one task at a time per clock cycle,
Yes.
we can do two tasks in parallel.
Yeah, makes sense.
That is what I'm.
Yeah, the thinking is perfect. So how do you replicate that in hardware?
So we need to have extra hardware, right? Extra
Yes.
hardware. So,
Yes.
so we need to have double hardware. So
Yes.
that extra hardware consumes extra energy.
Yes.
We might need extra power.
So it's like adding another circuit A in parallel.
Yes.
So that we achieve parallelism. So essentially, you told it's like more area, right?
Yeah, it takes more circuit and more area.
Okay.
But we can have faster throughput. Not.
So yeah, same thing.
Yeah.
Yeah, faster throughput. What you said is correct.
And because of that, now you're saying if we don't want faster throughput, we can reduce
Yes.
voltage. Okay.
Yes.
And then we can save power.
We can reduce voltage or frequency. We can save power. But yeah, the trade-off is like area versus power.
Okay, so I just wanted to have a little bit of clarification. So because now we have two elements, right? So like as you mentioned before, we have two circuit elements. So the power consumption is twice.
Yes, actually. So if you keep on adding that, of course, there will be a point where power exceeds the power of the before circuit.
Oh.
Yeah, what you pointed out is correct.
So what I think energy is same because either way we are doing the same amount of work, but the power is kind of double.
So depends. The energy would be decreased. What do you think if we reduce operating voltage or if we reduce the frequency?
No,
energy decreases.
I mean, let's say, not before if we decrease voltage or frequency. So let's say if through circuit element A, we need to do two tasks.
Okay.
So it might take two clock cycles and energy consumed is, let's say, E.
Okay.
Now, if we have two circuit elements,
okay,
we can so complete the tasks within one clock cycle within one clock cycle with one circuit A does my task 1 and one circuit A will do task 2.
Okay.
So replicating the same circuit A twice, so that the energy consumed for doing the same tasks either in two clock cycles or like in one clock cycle, but twice. How do you explain?
I got you.
Yeah. So
yeah, the energy remains same. So my question is, what do you think of power at that time?
Yeah, that's the power. Now we are doing instead of consuming energy over two clock cycles, we are consuming the same energy in a single clock cycle. So my power will be high, right? Increasing.
Yes,
Will be increasing.
completely makes sense. Yeah, perfect.
but the decrease in voltage or frequency should overcompensate this power in order to save power.
Yes, essentially that's it. So if we decrease frequency or voltage, and the power decreases, but yeah, essentially the main thing, the energy also decreasing, which is good. Yeah, if you want the same throughput as the before circuit.
Okay.
So that's it for parallelism too. I think that's it. Our gate this low power thing.
Thanks for watching the video. If you like the video, please do like, share, and if possible, subscribe to the channel.